Yes. People are still bringing online and in person, but let's get started. So we're at the penultimate colloquium for the semester. I hope you've had a good winter break, or fall break rather. I'm delighted today to welcome Yao-Yuan to our campus. He's a assistant professor at the University of Utah. He did his undergraduate work in Taiwan at NTU, before moving to Stanford for grad school. He moved on from there to Pittsburgh as a Lively Fellow, and then Rutgers as an Einstein Fellow before starting his faculty position. And he's been incredibly active in all of this time in the LSST Document Science Collaboration. That he's been Collaboration Council member twice. He started the Dark Matter Working Group and is sort of one of the world's experts on low mass galaxies, which he's going to be telling us all about today. And for his extensive sins, he's now in the desk management team. So yeah, please take it away.
Thank you, Gautam. And I blame Gautam for being the management of desk. Thank you all for being here. I had a great time, despite the snow, but I had a great, Pittsburgh trained me well. But really I had a lovely time this morning, afternoon, talking to you all. So I'm going to talk a little bit about low mass galaxies. Looking at the images here, there is some of the low mass galaxies that I've identified. Some of the things that the brighter ones probably have a stellar mass of like 10 to the 7, 10 to the 8. The fainter ones may have a stellar mass of like 10 to the 5, 10 to the 6. When I talk about low mass galaxy, I'm talking about a wide range of galaxy, all the way from like 10 to the 9-ish, that is roughly LMC mass, to all the way down to things like 10 to the 3, 1,000 stellar masses. Most of my talk will be focusing on things between like 10 to the 5 to 10 to the 8-ish, but it's a wide range of low mass galaxies. So I will try to specify whenever I can, but just so you know, whenever I use the term low mass galaxy for this image. I also mentioned cosmological question in my title. So when we think about cosmological questions, usually we think about the structure. Oh yes.
Dark matter masses or
stellar mass, galaxy stellar mass. But this segue into dark matter. So you're looking at the picture of like a simulated universe, if you can see dark matter. So this, you see the filamentary structure, you see these bright spots on the dark matter halos, and then you can see you see bright spot that galaxy cluster kind of like zoom. So this kind of things, oops. Galaxy clusters, this kind of large isolated halo, but you also see like a smaller dots. There are potentially places that can host like smaller galaxies. Sometimes I look at this picture, I feel like it's almost like a escape for us. Like being astronomer is such a privilege in that you think about the scales at like megaparsec, which is like nothing about this human world matters, which is kind of nice, right? Because like there are just so many things, especially right now, like that is pretty like difficult. And I think it's kind of weird time to do science at this time. And like, this is almost like an escape in that sense. Like you think about cosmological questions and you're like not worried about anything. I am a maintainer of the Astronomy Astrophysics list. So I've been doing this since about 2018. This is a list for people who are, professional astronomers to, if they are in the LGBT community and they feel comfortable being out, and they can be on this list. This list exists for a very long time, way before my time. This actually started in the 90s, and then it has been, existing for like more than 20 years. And I only just started to help maintain this list in 2018. And so starting 20, so here's like, there's a prehistory of our list. And I took over the maintenance in early 2018. And then since then, I keep track of the number of people on our list. So you're looking at the plots of people on our list, which is like people who identify as LGBTQ in orange, and then in the green, people who identify as allies. And so I'm showing you a trend as a function of time. And the 2025 is, the 25 hasn't ended, so it's just the number for now. So, there is something interesting here. One thing is that, people who are comfortable being out start to suppress the people's claim that they are ally, which is kind of cool. At some point that we also started to allow people to identify as transgender or non-binary. And so you can see like, the fraction of people who are, out and then identify themselves as transgender or non-binary also increase. The fraction itself also increased with time. That I thought is also interesting. I think it also hinted at that the people feel more comfortable in terms of identifying their identity as a function of time. Now, as an astronomer or as a physicist, when you have the chart like this, what you feed a line to it, right? So I feed a line with just the first 3 data points. For the reason that I want to see what does the trend look like if you compare to a linear trend. And so you see there is actually a little bit faster increase compared to linear trend until like kind of recently. And that dip, I would say, is actually real. It's not just because 2025 hasn't ended. So since my start of maintain the thing, occasionally I would get people saying that, sorry, please take me off the out list for various reasons. I got that about like once a year until about 2024. And in 2025 alone, I already received more than 20 requests of people needing to be taken down from the out list. Many of those people are from they work at the national labs or places like NASA Space Telescope, an OAO. Like if they have affiliation with the federal government in some way, it is more difficult and much more unsafe for them to be on the out list. It is really hard. Like I have to say, every single time I got an email say that I need to be removed from the out list, it's like it just feels like devastating. But I understand. I'm the person who actually email out. If you want, like some of you might even be on the list. Like I send out annual email, and nowadays in my annual email, I should remind people to say, hey, take a close look of your personal situation. If you need to remove your name, that's totally fine, and you should do that. But I started my talk with this just to kind of highlight that, it's weird nowadays when I go out to give colloquium to just like having this wonderful hour that I can just kind of dive into the science I love and then talk about all of it. But that sometimes feel like a little bit weird in like everything else is happening around us. And so I'm using this opening as just a kind of a reminder of where we are. And I do think part of the reason I'm doing this is that is also as a form of resistance. Like the fact that I'm giving the talk as myself, astronomer, that itself is a form of resistance and protest, right? And I hope to share that with you, that if you are in the position that you can do that protest, consider doing that if that you are able and feel comfortable doing so. Okay, so so that is what I was showing you just right before. And so I mentioned that we have, galaxy cluster and, galaxy group Milky Way-sized systems. And so this kind of structure is ubiquitous throughout the universe, obviously, if you believe in dark matter. One thing I want to kind of highlight, and I mean, I know that, you probably all know this, but just sometimes it's easy to forget. But when we think about galaxy and dark matter halo, they are at the very different scales, right? So the galaxies are really at the very center of dark matter halo. So here I'm taking an example of Milky Way-sized system. So that is the Milky Way-sized dark matter halo right there. And the galaxy of the Milky Way, the disk size is about like 1/10 of the dark matter halo size. Okay, so it's at the very center. And you can also see that within the dark matter halo's viral radius, you also have some other density peaks here. This we call the subhalo or substructure. And they also host galaxies. If you think everything is spherical, which you should, like a physicist, then we finally think about like the dark matter halo as the central dark matter halo, and you usually have the central galaxy live there, and then you then have the subhalos, and then you could have satellite galaxy live here. They call satellite galaxy because the subhalo are orbiting around the main galaxy, although that is not technically correct because it's really the dark matter halo of the main galaxy that have enough strong potential pull to make the subhalo and satellite orbiting around it. So I will be, this is just for me to explain some of the technology I'll be using, and I will, a lot of my talk will be focusing on the subhalo, and some of the subhalo, especially if they are orbiting around the Milky Way-mass galaxy, obviously then we'll have a low mass than the Milky Way galaxy, and so that's why we will talk about some of those things. So one of the reasons that the low mass galaxies are interesting is because they can potentially tell us about something about dark matter. So this is actually a white paper for the snow mass that people are showing that for different kind of, this is just illustration, but this is just showing that for different kind of dark matter model, there could be observables at the galaxy scale that you can observe different behaviors of the galaxy. It can be that you have a different density profile of the galaxy, you have different population, different numbers, and all sorts of things. More quantitatively speaking, a different dark matter candidates change the power spectrum, right? Because the dark matter candidate, if they have different behavior, they can introduce basically adjustments to the power spectrum that is predicted by the cold dark matter. So this is showing you an example. The gray line there is a cold dark matter primordial power spectrum, linear power spectrum. And then you can see if you introduce like warm dark matter or fuzzy dark matter, this is obviously specific model, so you can tune the parameter to change. But this is just showing you they can suppress the power spectrum. They could also enhance the power spectrum at some level. Now, I should say most of this on the right of this chart is still not yet observable. I mean, there are some specific experiments can do test on some of the small range of this final space. Most of the things that I will tell you about is, in this mass range. So, sensitive to things like non-dark matter, fuzzy dark matter, if they're suppressing the substructure. They can also impact the internal structure of the galaxy. So, for example, for self-integrating dark matter, they could create a core at the center of the dark matter potential well. They could also create a much denser core at the center, so you can form a core because the thermal equilibrium, and then at some point they will all collapse, so creating even the steeper core. So this is showing you how the on this left side is showing the potential density profile for NFW, which is the prediction from cold dark matter, versus self-integrating matter in the core forming stage versus core collapse stage. So you can change the internal structure of galaxy. So many of these things are interesting in that we still don't know what dark matter is. And then so if you can observe any of this small ping-pong signature, it will be interesting. But as you know, that we have not been able to do that, otherwise you will have heard of this on news. And part of the reason that is people have not yes, we have found we have ruled out specific dark matter model, is because it turns out galaxy formation is really complicated. And so if we look at relationship between galaxies, so I'm showing you galaxy stellar mass on the y-axis versus halo mass on the x-axis. Even in the region that we understand a lot, like the Milky Way is roughly here, and this is kind of like LMC, SMC. There's still significant scatter. Like this is kind of almost like 0.5 deck scatter in that region. And then once we go below SMC mass, we don't even know what the slope look like in that relationship. Like there's widely uncertainty in the region. This is the same plot, but just showing you in stellar mass to halo mass ratio on the y-axis instead. So again, Milky Way is the center. We now understand that this decreasing is mostly due to different kind of feedback mechanism. In the high mass end, mostly due to black hole AGN feedback. On the low mass end, multiple things can contribute to the suppression of star formation. And similarly, once you go below this mass scale, so this is again about like 10 to the 11 halo mass, 10 to the 8-ish in stellar mass. All these things are basically extrapolation from different models, and there's no clear census of how that should look like, as I said. And so that is one of the main reasons that it's difficult to directly use galaxy observable to construct dark matter, because whatever that you observe, you need to figure out the uncertainty from the galaxy formation cycle. And so that is kind of where I got like sucked into the low mass galaxy business. It's like, okay, so we don't know what's going on there. Can we, first of all, if we want to do all this, find enough observation so that I can even just like for first thing to figure out what is the galactic connection in the low mass end. Okay, so the first thing is like, well, let's just find out this low mass galaxy. So it turns out that is hard. Even though if you think about the mass function, there should be a lot of low mass galaxy. But the thing is, if they're further away, then you cannot see that. So you can only see close by low mass galaxy. So if you can only see close by low mass galaxy, that means the number density of low mass galaxies is actually low if you consider all the volume that you are looking at. So let me explain. And this is probably, if you're only taking one thing away from my talk, this is probably the thing I would think is most interesting. You all have obviously heard about Rubin Observatory, and you think, well, it's so exciting. Rubin data is going to be so great. It's so deep, such a wonderful thing. It turns out when you have better telescope, it's actually more and more difficult to find low mass galaxy. And the reason is that when you increase the depth of your telescope, you increase more volume in the background, then you increase the fainter object you can see in the foreground. And so if I plot the number of galaxies that you see as a function of the apparent magnitude limit of your telescope, this increase of basically is within the lower nearby region, and you are seeing fainter and fainter galaxies, does not increase as fast as all the galaxies now you can starting to seeing they are further away from you because you are now increasing the background like a light cone, which has a lot more volume. So at fixed apparent magnitude, the ratio of nearby, and so intrinsically faint galaxy to all the galaxies you can see at the same apparent magnitude decrease as you get better telescope. And this is not even Rubin magnitude limit, which is way over there. And so if I don't have distance information, at the fixed apparent magnitude, if I randomly choose a galaxy at apparent magnitude, the chance I got a low mass galaxy actually decrease as your telescope gets better and better. And so the main point of the rest of my talk is like, then what do we do? Like, how do you then find low mass galaxy in the event that you have better telescope that you can see more and more stuff? But yes,
It's for a point source.
Hmm?
For a point source, not low surface brightness.
well, when this particular plot, I'm consider integrated light. So like I think all the lights in the galaxy as a detection. So not necessarily just point source. But one of the things that I would say, like one thing that you can then distinguish between this if you don't have redshift is through the light profile though. Yeah. Yes. So light profile will be one of the hints that you can do to distinguish low mass galaxy versus higher redshift galaxies. But before we go into using photometric information, one of the ways you can beat this is look at the satellite system. So remember, like talk about this structure. So if you know there's a bright galaxy, then it's more likely to find low mass galaxy in a nearby region because there's overdensity of low mass galaxy due to the structure formation, due to the nearby satellites. So one of the ways that you can more likely to find low mass galaxy is through, if you know the bright galaxy at the center already, then you can just look at the nearby region and more likely you can find a low mass galaxy. And this is actually, people who are doing low mass galaxy business, obviously they know this. And so a lot of the work in the past decade has been focusing on satellite galaxies, that people look for satellite systems. This particularly if you're looking for galaxies at the 10 to the 9, 10 to the 8, 10 to the 7 stellar masses, then you want to find a host galaxy that is around the Milky Way-mass range, so that they host a satellite galaxy of those masses. And so obviously in the local group, these are just our own Milky Way and the M31. This is the easiest place that you can find those galaxies. In the Milky Way alone, we have already identified more than 60 satellite galaxies. And then we are still discovering those, like papers are still coming out of people finding new satellite galaxies in the Milky Way's virial radius, which is about 300 kpc. Once you go to M31, it becomes much more difficult because now the whole system is like 700 kpc away. But still, we find like tens of satellites in the M31 system. So as you move further and further away, the number of satellites you find each system drops. And not because there are fewer satellites in those systems, it's just because you can only see the bright ones. So once you go to local volume, you start to only see about 10 satellites per system. You see the 10 brightest satellites. Once you go to about like 25 to 50 megaparsec, you see about like 4 satellites per system. And if you go to like using SDSS, then you see about like at most 1 satellite per system for the Milky Way. So I'm talking about Milky Way type of galaxies in those regions. But at the same time, your volume increase. So the number of systems you can survey increase as you go further and further away, right? So you are trading off between the number of systems that you can study versus for each individual system, how many satellites that you can study.
Are those dots in each circle traces the actual radio distribution or just
No, they are not actually tracing the actual radio distribution. They are random visualization only. So the other thing I want to highlight is that in all this different mass regime, you actually have to kind of utilize a wide range of observational technique to find all these galaxies. So in the Milky Way, so when we talk about low mass galaxies in the Milky Way, it's actually a very different business in terms of how you find that compared to things like in the 25 to 40 megaparsec region. In the Milky Way, these things are so close that you can actually resolve the individual stars in the galaxy, or at least partially resolve or resolve the brightest one. And so in this region, most of the time that people do resolve stellar population studies, so you look at the red giant branch, and then you find the tip red giant branch to get distance. And in the most nearby region, like since we think about like 150 to 200 megaparsec, you can even do that with ground-based telescope. You don't even need to go to space. Once you move out to kind of like M31, you start to use, you can still do resolve stellar population, but sometimes you need to use space telescope to do that. And then once you move further away, the things become partially resolved. You only see 1 or 2 stars in the red giant branch. In those regions, sometimes you can still use space telescope to get like the tip or red giant branch distance. A lot of time that people need to use surface branch fluctuation. So this is looking at like how the light profile fluctuation will change, because that fluctuation will change with distance. The closer things are, the more fluctuation you will see. Right? It's similar to if you have a piece of paper that have writing on it. When it's close, you can read writing. When it's further away, you cannot read writing. So it's the same idea. So you can use that to kind of get a distance. But once you move even further away, all these galaxies are kind of a small blob in the sky. You cannot even get surface brightness. So there, really what you need to do is to do redshift, to get a galaxy redshift, right? But depending on which region you are on, sometimes you have to do a targeted spectroscopy survey because the area are too wide on the sky. So you have to kind of patch a specific region. Or if you are even further away, that is not even enough. So you need to just rely on wide scale, wide field survey, spectroscopy survey to get galaxies. So I want to mention this just because, when I will talk about each of this region a little bit. But, I want to clarify that they are using a very different technique in terms of how to find. So I will start with the middle part, SAGA survey, which is something that I've been working on for a long time. I started this joining this group since I was a grad student, all the way until like last year. So the SAGA survey is a survey that looking for Milky Way-like system, and then the way that we're doing it is like find a Milky Way-like galaxies and then find a satellite around it. Okay, so here is kind of what we do. We find a Milky Way-like galaxy or Milky Way-mass galaxy. And remember, the galaxy is much smaller than the vector radius of the dark matter halo. So we draw a circle that corresponding to roughly the radius of the dark matter halo. And then we say, are there any galaxy within the circle that is a satellite galaxy of the central galaxy? And by satellite galaxy, I mean that they should co-locate in terms of the redshift. Like the redshift should not be different by too much. Okay. So in this particular case, we do a spectroscopy survey. We basically get redshift for almost all the galaxy in this field of view to identify the satellite galaxy of this object. So that is challenging because, as I told you, there's a lot of galaxy in the field of view at a fixed apparent magnitude. So at SST, roughly SDS is apparent magnitude. If I take all the galaxy sources from a photometric catalog, there's about like 2,000 something per square degree. By the way, it turns out that the field of view for those galaxies roughly is about a square degree. So what we do is that we start to, so if you want to follow all of these things, it's not impossible, it's just very expensive because you need to write a lot of proposals to be able to follow this up. And we actually did that with like a few systems, like for 1 or 2 SAGA systems, we actually did that. And it was like, just like enormous time of like trying to do that. So we did a little bit, like obviously that would be kind of like ridiculous, and I would still be running this survey by now. So you can start to do something smarter. So first of all, galaxies have redshifts, which means if they're further away, they got redshift further into the red spectra. So at some point, they cannot be at the same redshift just because how far they have been redshift away. So you can do some color cut to get rid of things that's physically impossible to be a low mass galaxy or nearby galaxy. So that gives you about like half of those things. And then you can start to use something even smarter. You can start to use the color and the surface brightness information that to distinguish things that are more likely to be nearby and things that are further away. So from the stage 1 to stage 2, we are able to do that because we collect enough data for stage 1. So we have enough confidence that we are not removing galaxies that are truly a low mass galaxy. And then from there, you are getting about 4 galaxies per system. Like we waste a lot of resources on these galaxies. They are not completely wasted. I will show you why they are still useful. But in the end, you got about 4 galaxies per system. They are actually truly a satellite. Now, I know some of you who are just not believing us. Like, do you really need to spend so much spectroscopy resources to do that? So here are the 5 galaxies that I grabbed from the green points. So past 2 of our cuts. And then only 1 of those are a satellite galaxy. So the question is, can we tell with the photometric data only without taking a spectrum? So I would go to let you pick which one is actually the satellite galaxy. I would not ask you to vote. So you just need to know the answer on your own, and no one will be embarrassed. Okay, so take your pick. Only 1 of those is a satellite galaxy, and the other 4 are all background galaxy. And if you are interested, the redshift distance we are talking about is about 0.01. And all the other galaxies have a redshift greater than 0.05. So it's quite different if you care about low redshift objects. Okay, so you make your pick. Okay, and you don't need to tell me whether you get it right or wrong. But the right is the satellite galaxy is the 4th one. The 1st one from the right. Sorry, 1st one from the left. 2nd one from the right. It's this one. It's the satellite galaxy. Okay. So here's all the galaxies we have found through 101 SAGA systems. You can see we have very bright objects. They are LMC-like satellites, all the way to those tiny ones I just showing you on the previous slide. There's not much science from this slide other than they are all beautiful galaxies. I love to show them. But I also show you kind of a diversity of low mass galaxies. You can see some of these galaxies bulge. They are still bright enough. And some of those you don't, like some of these are just like fuzzy ground. And sometimes you got, every now and then you got like this very low surface size things. They seem to be massive, but they don't have any internal structure at the center. So put that into a mass function. So now I'm showing you the satellite mass function. This is how many satellites that is more massive than certain stellar masses. Okay. So each line, each colored line shows you the number of satellites as a function of stellar masses. So at a glance, you see kind of like a rainbow color gradient. And that itself is actually scientifically interesting because the fact that you see a gradient rather than just everything mixed together is saying that if a system are more likely to have a high mass satellite, it's also more likely to have more satellite at given mass limit. So it's not the slope does not always cross each other. They are like a scale length. That is actually a prediction for embodied simulation. If you think if I plot this in terms of subhalo mass rather than stellar mass of the dark matter, that is a very strong prediction from embodied simulation that in a system that you have massive satellite are more likely to have massive subhalo is more likely to have more subhalo in total. So the fact that you see this gradient in the stellar mass space is actually saying that the galaxy formation does not completely erase the information from the embodied. So the idea that larger galaxies live in larger halo on the zeroth order holds. Like it does not just like completely randomly assign satellites to halos. And so if we take a galaxy halo connection model like I showed you earlier, and then putting into an embodied simulation, you can roughly predict this to the zeroth order correctly. I also compare the Milky Way and 31 here. You can see the Milky Way line is this line. And then this is the M31. Now, pay attention to where they start. You are roughly in the kind of orange-ish place. And then when you go to here, the M31 end around the orange yellowish place. The Milky Way end and this blue purple-ish place. So this is saying that, yes.
Sorry to interrupt. The highest end of this mass range, I'm wondering if in your sample, are there sort of major mergers that you're including, or were there no major mergers in the sample, or did you remove those from your sample?
So there's we don't know if there's a major merger in the sense that, well, we don't have anything that are currently interacting. So all the central galaxy is isolated. But I don't know if they have major merger in the sense that I would not know, right? Like if they just come in recent, like if it's LMC, we would not have known because we don't have any orbital information at all.
Was that part of the sample selection, or was it just you didn't have any mergers that were happening that you could see with the tidal effects?
The sample selection is that we cannot have a galaxy that is kind of as bright as the Milky Way galaxy within the Vero radius. We didn't use tidal selection, so some of these things could have tidal effect. But I think I remember seeing all the hosts. I don't think they have very clear, strong tidal effect on the host galaxy. But the host galaxy itself is like much more massive than a satellite, though. So I think if any tidal effect, they will most likely show in the satellite. But we didn't exclude any LSMC-like cases, and so that's why we have a bunch of massive objects there. But one thing I want to point out is that the Milky Way is kind of unusual if you think about the Milky Way have LMC. Like it's not unusual in terms of just the number of satellites itself, but it's kind of unusual given the fact that it has LMC. And so it turns out that is not, well, it was actually kind of, the SAGA survey had run for like, almost more than a decade. So I think when we first saw this, we thought it was quite strange when we have a smaller sample size. And then we were not sure, we're building out the sample size. But in the past 5 years, this actually has been something that the community has now actually feel like we understand this much better. Like I did not know this 10 years ago. I think now people all understand that LMC SMC systems are also only joining the Milky Way quite recently. And so you can kind of think about the Milky Way as a system that is slightly older and actually less massive, because if you think about documented halo mass, if you take out LMC and SMC, the Milky Way is only about like 85% of the total mass of the Milky Way's documented halo mass today. Like LMC, SMC, the whole system take about like 10 to 15% mass, total mass in documented halo mass of the whole system. And so if I rewind before the LMC, SMC forming, the Milky Way's total mass is actually lower. The whole system is older because there's no massive satellite. So the whole system means the whole system is older. So it's not that surprising that it has a fewer number of satellites in total, right? And it's only recently that SMC, SMC join, so it become this strange situation that you have a massive satellite, but not that many satellites in total.
But in order to find all the Milky Way satellites, you need to observe the whole sky.
Yeah. Yes.
And are we certain that we have observed the whole sky and find all the Milky Way satellites?
Up to this mass range, yes.
Oh.
I think up to 10 to the 7, even 10 to the 6, people would say, maybe except for you happen to have a satellite right behind the disk. I think even when it is close to disk, we are pretty certain that we have found it all. But obviously, if we talk about like lower mass, like 10 to the 3, 10 to the 4, no, not at all. We are still like, that's why I'm saying like, even just 2 weeks ago, I remember seeing a paper like we find 3 more satellites in the Milky Way at the 10 to the 3. Yes.
I forget, we've never had this discussion of recently. Are there LMC satellites?
There's LNC also have satellites, yes.
And those are included in the count of Milky Way satellites?
Not to this mass range. So this is not that, like, so LMC is here, SMC is here, their satellite mass is much lower here. So not to this mass range.
So something like the LMC couldn't, you were talking about the halo mass being lower than it seemed because LMC came in. But that doesn't, the LMC and SMC don't boost the satellite number.
So yeah, so in my saw experiment, you're removing LMC, SMC, it wouldn't impact the satellite number to this mass range because their satellite are even more low mass. Was there a question there? Okay. I'm going to skip that part. So the other thing that we look at other than the mass function is satellite quench fraction. So this is the fraction of satellite they are not star forming. Okay, I don't know why it's not star forming fraction, but people like quench fraction. So it's 1 means that all the satellites are not star forming, 0 means all the satellites are still star forming. So here is what we are showing. This is quench fraction as a function of stellar mass in log. the Milky Way M31 is here. Like if you only plot Milky Way though, it's even more extreme. It's like star forming LNC, SMC, and then everything else is quenched. Now, there's small number statistics where, right, you only have like one satellite there. But roughly speaking, there's a sharper transition in the Milky Way M31 compared to if I average all the samples in SAGA. This is the green points here. This is the field galaxy, just for comparison, okay? So one thing you notice is that the SAGA things are slightly less quenched. They are more star forming, except for this very high mass N, where the Milky Way have this mostly coming from Milky Way. This point mostly coming from LMC and LMC and N33. Those are star forming, and so I think this comparison also just kind of collaborate with the story that Milky Way's the lower mass end of the Milky Way satellites are just slightly older. They are joining the Milky Way much earlier, and so they have been in the Milky Way potential for longer time for the tidal effect or redistribution effect to reduce the star formation of those satellites. While the SAGA sample, we have we sample all the possibilities. So we have some cases that has not happened, and some cases it has happened. So we bring the quench fraction down a little bit. And so this is another thing that I think 5 years ago, it was like when we first present this, I think in 2017 is the first time we showed this with only a third of our final data. And there was a lot of like debate in the field, like, is this true? Is this because the SAGA is biased? And like what's going on? And I think now people are just like, yeah, this of course we expect this because the Milky Way is. So sometimes it's kind of interesting to see the field progress. Like there was an idea that was not everyone accept, and now it's like everyone's like, yeah, of course. Like what are you talking about? Like we already know this.
So do your green lines actually show the complete range? And so you do have some systems that are actually quite high or low compared to the bins?
Yeah, so the green points is the average over all the SAGA system.
Right.
If I compare the system to system variation, it's shown as this thin line. This is to show you because the Milky Way M31 is only like 1 or 2 system, right? So in order to compare that, we also show if I just take the variation among systems. And so you can see the scale is large, right? Because you are now looking at the individual systems. But you can still see it's kind of like 1 to 2 sigma lower than the Milky Way. Yes.
What is the definition of your like quenched together? Quenched.
Great question. So it's a little bit complicated. So first of all, look at if there's any HL alpha emission. That is a clear indication of star forming. But even if not, sometimes we need to check because this is from a fiber, and this galaxy sometimes is larger than fiber. So we need to check the star forming region in the image. And then we also use NUV to see if there's any NUV star formation in the sample. And also sometimes in one of 2 cases, when it's ambiguous, in both cases, also H1 mass from the gas mass. I just say I could give like probably 3 talks if I just focus on the SAGA survey results, but I want to show you something else. So here are like some of the things that we found, cool things that we found on the SAGA survey. We have 3 papers. We have 5 papers and 3 from our final data release. So we have 2 papers from our earlier data release. So if you're interested, you can look it up online. So back to this picture. So I've talked about satellite galaxies, I talked about the SAGA survey to focus on this kind of systems. But remember, the reason I started this is because they are easier to find, right? We say that low mass galaxies is difficult to find. If you look at a satellite system, you're more likely to find them. So that's why we do this. But that does not mean the low mass galaxy, they're not in the satellite system, are not interested. They're just difficult to find. So now I come to move on to how do we find low mass galaxy that are not in the satellite system. So this is showing you, there's a few different things I'm showing you. First of all, the dots. This are, I take a simulation, I make putting some reasonable galaxy law connection, I'm making prediction of how the galaxy sample would look like in a nearby slice of the universe. One thing that I do is that all the colored points, so first of all, the color gradient is just distance. There's no particular size in it. But if you stare, you can see a few gray points. It might be difficult to see, but you can see gray points like here, 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 here. You can see some gray points here, here. The gray points are the points that are not low mass galaxies. All the color points are galaxies with a stellar mass less than 10 to the 9. So the point being, most of the filamentary structure are traced by low mass galaxies. And that is not itself surprising. In the filamentary structure, there are dark matter halos. And so if you populate a dark matter halo with galaxies, you should see that in the filamentary structure. It's just that high mass galaxies are easy to see, so we have been focused on those things. Not because the filament shouldn't have low mass galaxies. Well, in fact, if we go to find those filaments and we find no galaxies, that would be super interesting because then we need to figure out why the dark matter halo in those filaments do not form galaxies. But again, if you want to find those things, then you need to be able to find galaxies that are not associated with the more massive galaxy. And so on the lower part, okay, so let me first, so this image is just showing you again, in the inner region, very close by, you have resolved population, and then you start to have partially resolved, unresolved, but close enough that have very low surface brightness, to unresolved, but slightly further away, so you have a more concentrated light. So there's just a variation of different kind of galaxies in different regions, corresponding to kind of different observation technique that you need. So I already showed this earlier, but I also want to say that with newer telescope, what you do is that you actually be able to push each of the method to a wider range. So previously, we can only do resolved population with ground-based telescope to up to, maybe 0.3 megaparsec. And with LST, you'll be able to do that with like 1 to 2 megaparsec. So you are pushing each of the availability of the technique to a further away. And they also overlap more, right? Because as you push, so this is like the optimal range, but obviously they overlap with each other as you have deeper image. Yes.
For the quenched galaxy fraction, is it like related to their large scale structure? Like if they are like in the filament?
Good question. So the ones I show you are the satellite quench fraction itself.
Yep.
So for the satellite, most of it is due to the interaction with the main dark matter halo. So not necessarily with the filament. But we do find that, and I don't know if I have the plot to show, but we do find that if the whole system is in a denser environment, so it means they are more nearby larger system, the system quench fraction is also a little bit higher. The signal is not super strong, it's about like 1 sigma-ish signal, but we see a small hint of that the large scale structure definitely have an impact even for individual Milky Way systems. Okay, so let me show you just a few examples of what we can do if we want to find isolated galaxy. So I'm going to start with the inner region. So kind of in this range where you have resolved to partially resolved objects. So here is a patch of the sky. Can you spot an ultra diffuse, ultra faint low mass galaxy? Okay, so pointing at, like, look at where you think the galaxy is. Did you find it? Great. So this is the difference when you give a talk in astronomy department versus when you give a talk in physics department. So that is a galaxy that we found it in 2024, like just a few years ago. And it kind of escaped people because, as you can see, this is from dark energy camera. And so with this amount of sky area, you can even see by eye. But it kind of does not show up in any catalog. Like you see the individual stars, but it's very difficult to like do a catalog level search to find this object. If I plot the CMD from these objects, if I grab, so we'll see, if I go in and grab all the stars for the object, this is the same galaxy we're looking at, and then plot it. If you just plot those specific stars at that galaxy, you can see a region branch if you knew what you're looking for. But if you look at all the galaxies, so I overlay that star with just the star nearby, then it's kind of like hidden there. Like you can still make it out because I put them in orange points. But if you imagine you put all the blue points as orange, then it's very difficult to make out these particular features in that thing, right? And so the way that we actually find the size is actually not through the Ray-Jan branch thing. We just actually look at a simple stellar overdensity. And the reason that it got missed is that if you actually take a color gradient first, a color cut first, then there are so few stars, it's very difficult to pop out from the image. But if you just look at the stellar overdensity, then it's a little bit easier to find. So obviously, we are not, even though the Ray-Jan branch look pretty convincing, we are not, this is our first discovery throughout a series of discovery that we made. But this is the very first one, so we were very cautious. We do a HST follow-up. You can see the beautiful image HST. You can see this video start quite clearly. The Ray-Jan branch is super clear. You can even see the horizontal branch right here. And so you can measure quite a clear distance for the objects. And then we later find two other galaxies. So sorry, this should be an animation, but this is Leo N and Leo K. And both are found using the same method, stellar overdensity in DCAM. And then, and then you can see the Ray-Jan branch in space telescope data. So we're doing this just for trying to find isolated galaxies. Unfortunately, all three of these are not quite isolated. So the Pecos W is right outside M31's viral radius. So that dash line is the viral radius of M31. So I wouldn't call Pecos W an isolated galaxy. Just because it's slightly outside of our radius, gravity doesn't act like, let's just stop inference the galaxy if it's just slightly outside. So I would say the Pecos W mostly like has been inference. Sorry for this mess up, but the Leo and Leo K also just live outside the Milky Way's viral radius. But with this saying, we were, start to do a much broader search, and then we, this is like one of so we submit so far 4 HST proposal, and they all got accepted. This is like my most productive science kind of approach. And then we do find an isolated quench galaxy that Tareen Hai at Rutgers is working on the paper, and the paper should be on archive soon. So it's a pretty interesting object. It's quite isolated, that doesn't have any clear nearby neighbor. Yes.
So going from SAGA DR1 to DR2, you added in color cuts, and then you added in the surface brightness profile. And now you're using effectively space-based imaging to confirm this. From the AI point of view, this is just adding more features that provide more information. So why is the approach not, let's take all of Rubin data, combine it with Euclid data, and throw a machine learning or AI model at this to identify everything?
So first of all, the SAGA and these things are just different regions. So they don't quite combine the same way in that in this region, you are talking about, we find this by looking at individual stars versus if we're there, we're looking through getting a redshift of object. But I do agree with you, and I will show you a little bit in the unresolved region. I do think there is a way that we can get photometric information through either machine learning, AI, or whatever, that you get some distance information from the machine learning. And we have some preliminary result that I'll show you just in a bit. In the nearby region, the main issue is actually training set. Like the galaxy I show you, like the Pecos W, is like people always argue what is the first. So I would claim that it's one of the first galaxy that we find that is outside of Milky Way that has such a low stellar mass, like around 10 to the 4. And even today, I think outside of the Milky Way, from the 10 to the 4-ish stellar mass, we have less than 10 of those things. So it's like I have actually tried, we have tried machine learning, we use one shot for those, like you can train this fewer thing, but it's still very difficult for the machine learning method to pick up. And with that, I will say that, let me skip this. So by the way, this is just showing you what do we do with the stellar density. We do a pretty kind of, stupid thing. We do the histogram beaming and then trying to find the stellar density. Turns out that works quite well. And this has mostly done with one of the undergrad co-development who is leading this part of the work. And then we also do the fact that we don't have enough training data. So what we did is then we generate artificial galaxies. So because these are resolved stellar populations, so one nice thing is that if you assume some stellar population, you can then put that into mock observation and then generate artificial galaxy. So here you're looking at an image that's real on the right, an image that we generate artificially on the left. And you can kind of see the similar fuzzy structure at the center. You can see a stellar overdensity, and then you can kind of make out a red giant. There's a little bit more star here. You can kind of make out a red giant branch compared to this real data. And so what we do then is that we take all this artificial galaxy and then we put it into a CNN, a convolutional neural network. And then, so this is our test. We're still working on this, but this is after we do a first round of training, only using artificial galaxy. So all the training data are artificial. And then we run the model on the, okay, it's one of the galaxies we discovered. And then we got a probability of 0.996. So when I thought it was like, oh, this is like super interesting, like it seems to be we're solving the problem. Well, it turns out it's not that easy. So first of all, we have only 3 objects that are confirmed. They all have very high probability. They all are like 0.9 and above. But again, there's 3 data points. When I go in to look at all the galaxies that the CNN say is high that have not been confirmed, it's difficult for human then to tell if there is really a galaxy or not. And we go into a region where the computer says that there should be a galaxy, but like the human may not even be able to tell because this are indeed difficult. And I don't have enough Hubble Space Telescope time to confirm all of them. So we still need to figure out what do we do in those cases. But we do have some ideas, like, we can tune the way that we generate artificial galaxy to focus on specific parameters, a specific distance range. And so we can narrow down some of this, false positive further. So I hope I have some more like exciting result to show in terms of how we can use GMN to do this. But the initial result was quite encouraging, and we are really in the region which is like, it's about can we convince the review panel that our CNN is doing what we think it's doing, right? Because in the past, what we do is that we show some hint from the ground-based data that convince the review panel. But if we don't have that, but we have very, very convincing CNN result, is that enough to convince a review panel to say, give us time to confirm all these things? Alexis is also applying for grad school for those who might be looking for grad students. Okay, so I think I'm almost out of time, but just use a few more minutes to talk about this region. So let's come back to unresolved region and talk about what we can do in the future to find those things. So I told you that SAGA wasted a lot of our spectra, the redshift, on things that are not satellite, but they are not completely wasted, right? So if I look at a paramagnitude on the y-axis, and then redshift in the x-axis, the SAGA fill in this very difficult region, which they are faint and nearby, that we don't have a lot of previous spectra for. The color here shows that in each of the square, the percentage, the redshifts are from SAGA versus literature redshift. So that including SDSS and DESI. So you can see that, in this region, it's mostly from SAGA. And these are not a satellite galaxy. These are close to the satellite galaxy, like the ones that you were looking at, but just slightly further away. But they are still having a redshift at like 0.05. So like way below here. So there's a lot of galaxies that we got from the SAGA. So obviously that's a great training set, right? So you can then take it to do training and see what they give you in terms of their, let me show you that. Okay, so take all the data, we put in, again, using convolutional neural network. So on the left, I'm showing you the spectroscopy confirmed objects. Here, the high Z and low Z, first of all, I should say the high Z, low Z thing is like, you can choose whatever cut that you want, but I use 0.03 in this particular case. So everything above 0.03, I call it high Z. And for those who are actually working on high Z thing, just bear with me for now. And then we have things that are, things that we think ratio of 0.03, right? And then we then train this on CNN, and that is kind of the result that we got, right? And you can see there, the CNN is actually better at rejecting high redshift galaxy than confirming low redshift galaxy. And in part because of the sample size, you have actually much fewer things that are in the very low redshift region. And so that actually difference is still, again, sample size. And this work is actually earlier than the one I showed you earlier. So we haven't used any artificial galaxy in this particular work. And that might be another thing that we can show you. Yes.
What's the significance of 0.03? Because SAGA goes out to 0.1, right?
Yeah.
Why 0.03 or?
Not necessary. 0.03 is the range that we think is large enough sample that I will show you that we can do something cool that is using dwarf galaxy to do weak lensing. And so it's large enough sample that you can have enough dwarf galaxy in the regime. But there's no particular significance why it's needed 0.03. Like we have done this in several variations, 0.01, 0.03, 0.05. It's not that different in the result. So you might say, well, this is just CNN, but all these things on the right, the CNN predicted, but I don't know the actual redshift, right? Like I have not confirmed the redshift. This is not test data, this is like real data. So like, how do you know that your CNN is actually working well enough? So what we did is then, you all know DESI, which is amazing spectroscopy survey that have 5,000 fibers, and they use robot to precision them. They don't fill out all the fibers all the time when they target the signs. They have some spare fibers. So we've done the CNN, we went to DESI. I'm not actually even part of DESI, but we went to DESI and say, hey, you have some spare fiber. Do you want to just point at this random low mass galaxy and confirm that they are low mass galaxy? And they actually said yes. And so we send them like giant samples of things, but these are just feelers. So they are not going to be complete or whatever, but they will observe those things whenever they have a spare fiber. And so this is what we got. So this is redshift, and then this orange, green, and blue, the three things, the three tier that we found from our, the three tiers from our machine learning. So using the probability we got from machine learning, we make different cut of a tier because they asked us to give them the ranked list. So that's why. I should say that I should really make this plot in linear scale. It looks much more impressive in linear scale, just imagine, right? Because if you linear scale, the orange is really peaky compared to the green. But it really peak around like ratio 0.05, roughly speaking. But it does use the 0.03 cut when we do the machine learning thing. And that is the part that, in the range between 0.01 to 0.05, it's difficult to then further distinguish the distance. But you can do quite well to exclude things that are at like 0.1 and above. And so why do we do this at all? Obviously, finding this low mass galaxy are interesting in many reasons. And the most kind of my recent interest is, well, in part thanks to Decker, like I started to get interested in like the transients associated with those galaxies, like including AGN, TDE, supernovae, and stuff. But if you remember at the very beginning of my talk, my motivation of this is like understand dark matter physics. So when I was in Pittsburgh, I organized a dark matter conference. So the Carson mentioned that I created the dark matter working group in the LSST. And that is because we started this conference thinking about what can we do with Rubin without a lot of spectroscopy resources. What kind of dark matter science can we do? And I remember at the conference, I sit down with a few weak lensers, including like people like Rachel Mandelbaum. And I'm not weak lenser, but I do low mass galaxy. I was just like, can we do weak lensing with low mass galaxy? And they were like, it's going to be hard, you need a lot of them. But we're like, well, we can have a lot of them with Rubin. So we did a calculation and we're like, okay, it's actually potentially possible. And so what we're going to do is that we're going to, instead of one massive galaxy doing a lensing, we're going to stack the low mass galaxy and create a lensing signal. At that time, we thought this is going to be super difficult, like it's not going to be possible. To my surprise, people then take what we so this case, people take the SAGA redshift, train a different machine learning, just because, when we do the CNN, it was like 3 years ago, there's super old by now. So now people are using more advanced tool, like this is self-organizing map. But this idea is the same. They take all the SAGA redshift, and then they put in a self-organizing map, and then to get a distance estimate, and then this is translated to stellar mass, but it's the same thing. You get a distance estimate, then you can get a stellar mass estimate. You get a stellar mass estimate of the things, and then you use, in this case, just DS, using dark energy survey to see if there's a weak lensing signal. And they found a weak lensing signal. I was actually very surprised. I thought they would not be able to see anything. But here is the signal. This is just the actual shear signal. And this is where they live in the stellar mass halo mass relationship. And you can see this is, they predict a slightly higher halo mass for the stellar mass they are in, roughly. And then this compared to other prediction, we are about like 0.5 sigma away of the mean relationship. So we have not been able to actually measure density profile, obviously, but even being able to see a halo mass signal is quite exciting because that means that once you have a better source galaxy, then you can potentially measure the density profile of the sample. This is completely using the photometric selection. Like we use the redshift data for training, but there is no redshift information going to the measurement. Yes.
What is the number density of a source in your for this sample?
For the source, it's the same as the DS year 3 gold sample, but I don't remember what's the number.
Okay.
And the length is roughly like I think 30-40 thousands. There was just recently people repeat this experiment by using redshift indexing. So instead of using photometric sample, they use a confirmed redshift sample to do dwarf galaxy lensing, and they actually see signal completely agreeing with the photometric thing, which I also find very surprising because I was like, okay, this is great, very encouraging, but if I'm very completely honest, like I don't know about the contamination, like are you mistaken massive galaxy, all that. So I was again surprised when the people repeat the whole thing with DESI and actually basically get exactly the same signal when you use the clean, well, I guess as clean as it can be redshift sample. And so this is really nice because then it gives me hope that with Rubin that we can really do something really cool with the sample of low mass galaxy.
I'm a little bit of a computer here. So the SAGA sample is the satellite galaxy sample. So and the with lensing, the shear measurements give you the halo of the main galaxy. So what stellar mass are you plotting here?
Yeah, so the SAGA sample is only used to get the training for the redshift of objects. So supposedly most of these things are not satellites because then we apply to the whole sky or the sky that we have photometric data. And then most of the galaxy is actually more likely you find isolated galaxy than a satellite galaxy if you think about the whole sky. It's just they are rare in number density speaking. Now, when we translate into the halo mass, you are correct that some of those things are still going to be satellites, so they will contaminate the signal. So from this point to that point, we actually need to go through an embodied simulation and model the satellite in those signals and take them out when we translate into the halo mass. And so that will mean that we will. So another product of this result is the satellite fraction in our sample. So you will know how many satellites there is in order to get the lensing signal. So this is already taken into account of taking out the satellite in the sample. And just for completeness, this is our, so I mentioned that we have a conference at Pittsburgh. This is the original prediction we made in Pittsburgh. So this is the lensing signal you see with very optimistic assumption of being able to find all the low mass galaxy that Rubin were able to find. Then we were able to see some difference in the density profile. So not only you can measure the halo mass, but you can see difference in the density profile between say NFW and core NFW profile. And so that gives you ideas about the galaxy, the dark matter density. And I should say, sorry, this is the halo mass. So compared to how I just showed you, this is actually lowering stellar mass of what I just showed you earlier. So what the current measurement is slightly higher, about like 0.5 times higher than the halo mass shown here. So the idea is that Rubin will go to even fainter galaxies and being able to do this. And not only get the halo mass measurement, but also the density profile measurement. I should say that when we made this plot, this is with year 10 Rubin data. So not something that we can do like next year. But still, very promising. I think there will be a lot of people being done, even just with the first few years data. And I'm closing just with this plot. So this is showing kind of just give you a sense of what we are looking at here. Like the SAGA survey I mentioned, this is like satellite galaxy only. And I also even put Milky Way satellite on this plot to kind of give you like the SAGA survey find about like, order of magnitude more satellites than the Milky Way just because we have more systems. With LSST year 10 in the unresolved region, we will jump to that blue line here, assuming we have a good photometric way to identify low mass galaxy, right? And by the way, the number is done in things of 0.5 dex. So if you can just add up these points in each of the 0.5 decks, and that gives you almost like a million galaxies in the unresolved region itself. In the resolved region, the Rubin will give you roughly in this range, so about like again about order of magnitude more in the Milky Way. We also have a Rubin, which is also a wide field for the metric survey, and Rubin being in the space have better PSF. So in the unresolved region, it actually works better than Rubin. Rubin is smaller than Rubin, but combining the depths, like the better PSF and the smaller range, the number that Rubin will find will actually be similar to LSST in the resolved region. So this is super exciting. And you might ask, what happened in this gap? Like, why the line are not connected? And that is because in the partially resolved region, no one knows what to do. Actually, I kind of just like sweep that under the rug. But in this region, really the main issue is like for the Rubin, we need to get better star galaxy separation. We need to understand detectability. So a lot of people are working on this. I'm not too worried in this region, actually. I think there's great progress. In that region, we need better distance measurement with spectroscopy only, for the metric only. So thinking about targeted spectroscopy survey, train new AI machine learning method to get distance. I think a lot of progress we made. I'm slightly worried, but not the most worried part of all this chart. The middle panel is like, I have no idea what to do because the light is not enough to do, this kind of distance measurement, and the result population is not enough to do tip origin branch measurement. And so this is a new region that, I think we need new methods. And like, in the documented working group in desk, we are thinking a lot about like, how do we deal with the partially resolved region? Because, obviously you don't want to have a gap in the final stellar mass mass function that you are finding. So with that, I will conclude. I'll just show you my summary slide and happy to take any more questions if you have. Thank you. Questions?
Thank you for the talk. So from the SAGA survey result, do you find any interesting things about the morphology of the 12 galaxies?
Yeah. So we found, let's see, one of the things we found that, well, it's not necessarily morphology, but so once we look at its galaxy size as a function of galaxy mass, we are looking at the galaxy size, galaxy mass relationship. And what we find is that the SAGA, which is the purple line here, offset with the background. So SAGA background is basically everything that we rejected from Redshift. And then the SAGA is the one that actually satellite. So there's a slight offset you can see there. And then that trend is even more apparent if you take isolated. So SAGA background is just any background. So it can be a satellite or not a satellite, mostly not. Isolated is really isolated one. So we make sure there's no bright galaxy within like 1.5 megaparsec. Okay, so really isolated one. So we do see a kind of, again, about 1 sigma trend between the size mass relation of galaxies that are in an environment versus not in an isolated environment. It kind of, confirms. I'm a little bit worried about interpreting this too much because there's some confirmation bias, but it roughly consistent with our idea that when a small galaxy go into a larger thing, it will puff up because of tidal effects. And so we are actually going to look further into their morphology, like beyond size. Do we see asymmetry in the light profile? Do we see tidal feature and things like that?
Other questions? So you've talked about sort of the analysis from Rubin and then the space telescopes as almost like a follow-up instrument to confirm what you did. There's giant pixel processing that you would all do in the partially resolved area.
Yeah, I do think the partially resolved result, like joint processing, might be something to go. I think the other thing is that I think that one of the reasons partially resolved region is now that it's just like it's different community. Like I happen to be also in the resolved community and the unresolved community. They don't necessarily talk to each other. And so I think the other thing is like we need to also do catalog level search that correlate with the image level search. And that has not happened a lot. Like people either take the catalog and do catalog level search or like take the image. And I think that's another thing that we can do is to correlate those, just like not even with the joint pixel processing, but just even within Rubin, like having that information. So I don't know, I do think this is like something that people start to pay attention to as people are like, oh, realizing that. The thing is, like partial resolve region was so small right now, it's roughly only between like 1 to 5 megaparsec. But with Rubin, the partial resolve region between like 5 to 20 megaparsec. So it's a very different volume. So I think people will care a lot more about partial resolve region once we have Rubin. Yeah, go on.
This may be a naive question, but, so in the past, there was a missing satellite problem. And that I've heard recently about like too many satellites. So what is like the current consensus of that? Like with all the results?
So I think most people will agree, most people in this field will agree there's no missing satellite problem. I think that part, everyone agrees, okay? What is happening with missing satellite problem is just that the number of subhalo does not equal number of satellite. Like as you go down with stellar mass, you don't have, like not all subhalo are occupied with a galaxy. Now exactly how that transition works, still something we don't know. The too many satellite problem is a little bit strange. I'm not quite sure. So there is some observational evidence. I mean, even in the SAGA survey, we find that there are sometimes we have one sigma tension with simulation prediction about many satellites. I actually think that has something to do with simulation, not with observation. I think that our understanding with the galaxy-level connection is not actually as complete as we thought, especially in the low-mass region. So I think this is going to be too technical, but I think what happened is that the relationship is not as shallow as let me see if I can get one of that plot. I think this is probably not as shallow as we think, because when people have done this does not take occupation fraction into consideration. In that it assumes that every payload has a satellite in it. So if you take that into account, then you can make this actually slightly less shallow. And then you have just some empty subhalo. And so then in the system that you don't have empty subhalo, you will see more satellites. So that's but I should say this is my personal view. That is not a community consensus. I think in that regime, now people are doing a lot more with simulation, hydro simulation, to get a better sense of that.
There are also too big to fail problem, like
there's also too big to fail. There's also too big to fail. I also think so. Like missing satellite, I think 99% of the people in the field will say there's no missing satellite. Too big to fail, maybe 80% of people will say there's no too big to fail. So too big to fail, I think 80% of people will say is solved by consider baryonic feedback. Then you don't have too big to fail. I think 20% of people still argue, well, but then the baryonic feedback, you don't really know if they are bursty. Like it only solves too big to fail if the baryonic feedback is bursty. And so people are like, well, but if it's not bursty, then there's still a problem. I personally don't think there's a problem. I think the too big to fail is just a different manifest of again, similar to this, like if you have baryonic feedback, it will just make the scatter great here. In that you have some halo that have much lower stellar mass. But if you take the median relationship, you actually make the median relationship up. But you just scatter a lot more, I think, to the lower ones. So the average will probably still be there, but it's just a bigger scatter in the whole population. But again, I think 20% of people in the field might not agree with me. If you are interested in the most recent cold diamond challenge, I encourage you to look at planet of satellites, which I didn't talk about, but this is not the newest thing that people say, well, the planet of satellite is the thing that kills cold dark matter, which I also don't believe. But again, this is the new too big to fail thing.
What's that?
The planet of satellite is saying that the satellite in the Milky Way and the N31 has a coplanar rotation structure. And I can say that in the SAGA survey, we find no evidence that is the case.
And the idea that the LMC and SMC are on their first passage to the Milky Way, would that also kind of reduce the attention?
Yeah, but this is still a debate. So once we go to planet satellite, I would say 50% of people, maybe it's 50-50. So I'm on the camp saying that is not an issue. Like we already understand, but there are some people that still very much think that is an issue. But this is the part that I find it really actually we're seeing the progress of the field. Like I think maybe 10 years later, if I come back to give a talk, maybe we will have an understanding of what is going on with the planet of satellites.
All issues are created by people, not by nature.
You ask questions, okay, so you, okay, in that case, let's thank our speaker again. We are running around all day, so we should better get him some baryonic feedback in the form of dinner. If you'd like to join, meet us in the lobby in about 15 minutes. All right.